Hello everyone, my name is Dong-kyung Kim from Naver. Today I will give a speech about scheduling containers rather than functions for function as a service. This is the work I did with my colleague Hyun from Naver Cloud. Before we get started, let me briefly introduce myself and my company. Naver is operating many platforms to support many services and also provides them as a public cloud services. And I'm working on fast platforms, which is based on Apache OpenWhisk since 2017. And I am a PMC member of Apache OpenWhisk, and there are also 4 more committers in my team. So serverless computing is increasingly popular. One of the reasons is that maintaining servers is not easy. It's painful. So if we don't need to take care about server operation, then we can focus more on the business logic. If you look into the serverless section of AWS, there are many products and services. But today, I will give a speech about the function as a service only. The first one is background. In our work, we have focused on some types of workloads. And the first one is a multi-tenant workload. As a fast platform provider, we have many different tenants, and they invoke many different functions. To invoke these functions, fast platforms generally require many sandboxes, such as containers. So our work has focused on problems of workloads from multi-tenant. The next one is highly concurrent workload. According to the Charette et al. In 2020, small percentages of functions occupy 99.6% of the total invocations. It means that most invocations are comprised of highly concurrent workloads, and our work also focuses on them too. The next one is resource-intensive workload. Generally, the same function requires the same resource. If we schedule functions requiring same resource into the same worker, then this is bad for performance. So our work has focused on distributing heterogeneous workloads on each node to balance the resource usage. In this way, our work has targeted these 3 workloads. And before we talk about performance, let's look into the general architecture of fast cluster. One thing to note here is workers create and initialize the sandbox at the invocation time. So it means that invocation time may include the sandbox creation and initialization. And we call this cold start. And if an already initialized sandbox is reused, then we call it warm start. Surely warm start is much faster than cold start. Many articles are comparing the performance difference between cold start and warm start. If you look into the y-axis, then you can easily get the performance difference. But generally, warm start is 1 or 2 orders of magnitude faster than cold start. And we can easily expect that cold start is highly related to the performance. So there are generally 2 approaches to deal with cold start. First, a major one is microscopic approach to shorten the cold starts inside the virtualization. And another one is a macroscopic approach to reduce the number of cold starts by scheduling. Recent research work has mostly focused on a microscopic approach. This microscopic approach is indeed a direct way to resolve the root problems of cold start. We believe there is room for the performance improvement because fast platforms work over a cluster. There are few research works available for the fast scheduling. The first one is package-aware scheduling, which is based on caching of Python library and hashing, but it only works with the Python library. And Eugenics paper 2020 reduces the cold start of intermittent functions, but this is not general for our workloads that we presented previously. First of all, any of them rarely answers the following questions: how to schedule function requests to existing containers, and how to provision containers according to the characteristics of workloads, and how to remove the provisioned containers. So let's look into the scheduling problems by analyzing the existing fast scheduler. This is how OpenWhisk works. So controllers receive the function requests from users, and controllers schedule the request to the queues of each worker. So here it is important for controllers to schedule the function request to a container in the workers, and that is the scheduling. Controllers push function requests to workers queue. And to my knowledge, most fast schedulers are push-based. One good example can be AWS Lambda. According to the speech at the reInvent 2018, we can see that AWS Lambda is also working in a push-based way. And in the push-based way, it is very critical to select the right worker to push requests. Apache OpenWhisk uses a hash-based approach. So controllers use a hash function to select a worker to execute the function. Therefore, each function has its own designated worker. In this way, multiple controllers can easily select the target worker without any distributed decision. But the hash-based scheduling has multiple problems. First one, multiple functions can share the same hash value. Then they will be scheduled to the same worker. While other workers are idle, they will compete for the limited resource. Also, in multi-tenant workloads, more hash conflicts happen as more and more functions are executed. In turn, overall performance is degraded. The next problem is the response time is not deterministic. When a controller schedules a function 1 to a worker 1, if there is an available container, then it will do the warm start. But if there is no container, then it will trigger the cold start. And if there is no available container, also there is another container for other function is taking up the place, then it should first delete the container and do the cold start. If we compare this with the warm start, it's much slower than warm start. It's also worth noting that provisioning and deleting containers result from the worker status, and it makes response time less deterministic. The last problem is controllers do not wait for busy containers. So in this case, even if the hash value of function 1 is 1, this function request will be scheduled to the worker 2 because there is no available resource in worker 1. So worker 2 will create a new container and do the cold start. So it will take around 200 milliseconds. But what if the execution time of function 1 is only 20 milliseconds? Then the busy container will be available after 20 milliseconds. Then function can be executed after 20 milliseconds. If we compare this with a cold start, then it is at least 1 order of magnitude faster than cold start. So in many cases, waiting for busy containers may be faster than a new cold start. Then how can we improve the function scheduler? So hashing is generally bad for load balancing. Then what if we don't use hashing for scheduling? If you look into this diagram, it's very intuitive that we can collect all the container status and schedule this function request to worker 1 because there is available container for function 1. But it's not that simple in the real world. This is because one function can finish its execution in 2 milliseconds in the minimum case. It means that container status can last very shortly. So status can change very quickly like this. So when a controller scheduled this function request to the worker 1, this container status can change right after that. Also, there are multiple controllers, so they may schedule the function request to the same worker for the same container. So controllers should know the decision made by other controllers, and this is a distributed decision problem. To sum up, it's very expensive to maintain the container status and decision among controllers in real time. Of course, it can be implemented, but we believe it's not that efficient. So we took a different approach. Please note that container status is required for controllers to schedule, to push function requests. So if controllers don't push requests, then we don't need to maintain the container status in real time. So we changed the order from the push-based one to the pull-based one. So in our scheduler, each container pull each corresponding function request from the queue. So we named it as function pulling containers. So at first, controller just forwards the request to its function queue. Since there is no container, our scheduler provisions one container, and container pull the requests, and it will execute the function. And after the execution, it will pull the next request and execute the function again and again. And if this one single container is not enough, then our scheduler asynchronously provisions more containers. Then now it's very important to decide when and how many containers to provision. In our scheduler, container provision happens when there is no container and there are not enough containers. Not enough here means the number of requests in a queue is more than the throughput of existing containers. And if any requests have waited too much in the queue, then we consider it there are not enough containers. So let's say the execution time of function 1 is 10 milliseconds, and the interval to check the queue status is 100 milliseconds, and there are 10 requests in the queue. Then one container can handle 10 requests in the interval, and it can handle all 10 requests. But if the execution time of function 1 is 100 milliseconds, then one container can only handle one request in the interval. So we need 10 containers to handle these 10 requests. So we can calculate the throughput by execution time divided by the interval, and the number of required containers by the number of requests divided by the throughput. So at some point, if there are 3 containers, then we can provision 7 more containers. Then how can you know the execution time of the given function? In our scheduler, when each container pull a request, they send a previous execution time. And our scheduler stores the execution times in a circular buffer, so we can calculate the average execution time of recent n executions. In this way, container provisioning happens when there is no container and there are not enough containers. And regarding the container deletions, containers spontaneously vanish upon timeout. So let's say there are 10 incoming requests per interval. Then one container can handle all 10 requests. But what if we over-provision 9 more containers for some reason? Then this one container will handle all requests, and the other containers will suffer from starvation. This is possible because we introduced a priority queue. This priority queue prioritizes a fetch request from container with container ID. So only containers with a higher priority are served. So in this way, we schedule function requests to existing containers with the function pulling containers by pull method. And we provision containers according to the number of requests. Our containers spontaneously vanish with starvation. So we can keep the required number of containers. Next one is evaluations. The implementation we used for evaluation has been running in production for 2 years, and we are contributing back to the open risk. And in evaluations, we compare the FPC scheduler with the hash-based scheduler. This is because there is no other available scheduler for fast platforms. And we generated the workloads because it is more efficient to show the characteristics of scheduling algorithms. So we used 3 VMs for controllers and 3 PMs for Kafka and FPC scheduler, and 8 VMs for workers. And we used ngrindr to generate the traffic. The first one is multi-tenant test. We increased the number of function types from 1 to 64, and we utilized 100 virtual clients, and we measured these metrics. The average setup time here means how much time each request has waited before the actual execution. As we increase the number of function types, the request per second of a hash-rate scheduler was dramatically decreased. On the other hand, the FPC scheduler shows a steady level of requests per second. One thing to note here is FPC scheduler is not fully saturated. And as we increase the number of function types, more hash conflict happened in the hash-based schedulers. So there were more number of cold starts. Accordingly, it took more time to execute functions. The next one is concurrency test. We used 4 functions, and we increased the virtual client from 1 to 1,000. As we increased the number of virtual clients, the request per second of FPC scheduler was increasing and finally saturated with 1,000 controllers. But the request per second of hash-based scheduler was increasing until only 30 virtual clients. After then, it started fluctuating and finally decreasing after 400 virtual clients. The next one is resource contention test. So we designed 3 different types of functions for CPU, disk I/O, and network, and we generated requests for 10 minutes. Since the same functions share the same hash value, it's not surprising that CPU utilization of hash-based schedulers are skewed like this. And FPC scheduler randomly create the containers, so the standard deviation of FPC scheduler is relatively high. And the same pattern is observed in other resources as well. So disk utilization is skewed in hash-based scheduler, and it is same for the network utilizations. Since same functions compete for the same resources, there were more cold starts in the hash-based scheduler, and the execution time was slower in the hash-based scheduler as well. The next one is scale-out test. We increased the number of workers from 2 to 8, and we utilized 4 functions and 110 virtual clients for hash-based scheduler and 1,000 virtual clients for FPC scheduler. And this is because the 2 schedulers would require a different number of virtual clients to saturate the system. The throughput of FPC scheduler was mere linearly increasing as we scale workers, but the throughput of hash-based scheduler was not increased, no matter how many workers are added. So we talked about 2 approaches to improve the fast performance. Most researches have focused on shortening cold start, while few researches are available for fast scheduling. We introduced a pre-based continuous scheduling that does neither require real-time synchronization nor distributed decision. We provision and remove containers according to the number of requests, and we show high and stable performance for multi-tenant, highly concurrent, and resource-intensive workloads. Thank you for listening to my speech.